A portion of this video was sponsored by Norton 360.
Classical mechanics is great. If you know the state of a system, say the position and velocity of a particle, then you can use an equation, Newton's second law, to calculate what that particle will do in the future. In quantum mechanics, if you know the quantum state of a particle, that is, its wave function, you can use the Schrödinger equation to calculate what that particle will do in the future. Usually, it spreads out over time as it is doing here. Note, to make this animation, we really solved the Schrödinger equation. So there's a beautiful symmetry here. If you know the initial state, you can use an equation to evolve that state smoothly and continuously into the future. The problem is, in quantum mechanics, we never actually observe the wave function like this. Instead, when we measure it, we find the particle at a single point in space. So how are we to reconcile the spread out wave function evolving smoothly under the Schrödinger equation with this point-like particle detection? Now, I think it's understandable that when the founders of quantum theory approached this problem, they considered the measurement more real than the wave function. After all, the measurement was something we had actually observed, and it matches our experience of a world of matter particles. It was harder to say what the wave function was exactly. Schrödinger formulated his wave equation because scientists, notably de Broglie, suspected that matter has wave-like properties. But it took a third physicist, Max Born, to propose how we should interpret the wave function. At each point in space, the wave function has a complex amplitude, essentially just a real number plus an imaginary number. Max Born suggested if you take that amplitude and square it, you get the probability of finding the particle there. The fact that you have to square the amplitude actually appears as a last-minute footnote in Born's paper, but that is how probability was introduced into the core of our picture of reality. That's a pretty big philosophical leap. I mean, no longer is the universe deterministic. This made a lot of scientists, especially Einstein, uncomfortable. But the Born rule, as it is now called, remains at the heart of quantum mechanics because it is spectacularly successful at predicting the outcomes of experiments. So the way quantum mechanics came to be understood, and the way I learned it, is that there are two sets of rules. When you're not looking, the wave function simply evolves according to the Schrödinger equation. But when you are looking, when you make a measurement, the wave function collapses suddenly and irreversibly. And the probability of measuring any particular outcome is given by the amplitude of the wave function associated with that outcome squared. Now, Schrödinger himself hated this formulation, which is actually why he invented the famous Schrödinger's cat thought experiment. Put a cat in a box with a radioactive atom. Add a radiation detector that triggers the release of poisonous cyanide gas. Now, although it was only meant as a thought experiment, Schrödinger helpfully notes this device must be secured against direct interference by the cat. Anyway, the whole point of the experiment is to magnify the state of the atom up to the state of something macroscopic and tangible. He could have picked anything. It didn't have to be alive, but Schrödinger selected a cat. If the atom decays, the detector detects radiation, releases the poison, and the cat dies. If the atom doesn't decay, the detector doesn't detect radiation, poison is not released, and the cat remains alive. Since the state of the cat and detector apparatus are directly tied to the state of the atom, we say they are entangled. Where things get weird is that according to quantum mechanics, the state of the atom does not have to be either decayed or not decayed. Generally, it's in a superposition of both, decayed and not decayed at the same time, assuming no measurements have been made. This superposition state of the atom gets entangled with the detector, and then the cat. So after some time, the wave function of everything inside the box is in a superposition of the atom has not decayed, poison not released, cat alive state, and the atom has decayed, poison released, cat dead state. So according to quantum mechanics, the cat really is both alive and dead at the same time. Only when we open the box and make a measurement does the wave function collapse and the cat actually becomes either dead or alive. These days, Schrödinger's cat is often used as a way to show how weird quantum mechanics is. But that wasn't Schrödinger's point. He wanted to show that quantum mechanics, as formulated, was wrong. So Taking up Schrödinger's argument in this video, I want to show that there is a better way to think about Schrödinger's cat. In fact, a better way to think about quantum mechanics entirely that I'd argue is more logical and consistent. To get there, we have to examine the three essential components of Schrödinger's cat: superposition, entanglement, and measurement, to see if any of them is flawed. Superposition is the idea that quantum objects can be in two different states at the same time. This seems like a crazy idea and something we'd never observe, but we do indirectly with the double slit experiment. Fire individual electrons through two slits at a screen, and the pattern you see is not just the sum of electrons going separately through one slit and the other slit. It is an interference pattern. We are forced to conclude that a single electron somehow goes through one slit and the other slit simultaneously. This is superposition. Of course, it's easy to understand superposition with waves. They are spread out in space. And it's clear how the peak of a wave from one slit cancels with the trough of the wave from another slit to produce the interference pattern. And luckily, we know that when we're not looking, electrons are represented by a wave, the wave function. The double slit experiment then is concrete evidence that this wave enables individual electrons to pass through both slits at the same time. So superposition is on solid ground. The next concept is entanglement. Consider two electrons fired toward each other with equal and opposite velocities. We know they will scatter off each other, but we don't know exactly how. Their trajectories are given by spread out wave functions that only give us probabilities. But as soon as we measure the momentum of one of the electrons, we immediately know the momentum of the other one. It must be equal and opposite, otherwise conservation of momentum would be violated. Now, this may seem obvious, but consider that before the measurement, the momentum of each electron was in a superposition of states. Measuring one instantaneously collapsed the wave function of the other. And this would be true even if those electrons were light years apart. These electrons are entangled. What's really going on here is that after interacting, the electrons do not have separate wave functions at all. They are described by a single wave function, and this is what it means to be entangled. This explains why measuring one immediately affects the state of the other one, because the single wave function has collapsed. In fact, if we were being rigorous, we'd have to say that there is only one wave function, the wave function of the entire universe, which includes absolutely everything. But in the case of isolated, unentangled quantum particles, we can reasonably talk about their individual wave functions. And then once they interact with something else, entanglement is the result. So what we've seen is superposition is really the same thing as describing systems with waves. And entanglement means that after particles interact, they are described by a single wave function. These are fundamental parts of quantum theory, describing systems with wave functions that evolve according to the Schrödinger equation, which leaves only measurement. Remember, the measurement postulate was added as a second set of rules to connect the mathematics of quantum mechanics to what we actually observe. But doesn't it seem weird that there should be one rule for how systems evolve when we're not looking and a different rule for when we are? When you boil it down, measurement is just the interaction of one quantum system, electrons and photons, with another quantum system. And we know exactly how to deal with that. We simply evolve their wave functions according to the Schrödinger equation. So what if we throw out all the rules associated with measurement? Well then, in the Schrödinger's cat thought experiment, the radioactive atom in a superposition of decayed and not decayed gets entangled with the detector and in turn the cat. Now remember, we are also made of electrons and atoms which obey the laws of quantum mechanics, so we are quantum mechanical too. So when we open the box, there is no measurement, no wave function collapse. We simply get entangled with the state of everything inside the box. So we see the cat alive and we see the cat dead. Now, how is that possible? I'm guessing you've never seen both an alive and dead cat before. But the solution is, it's because the you that saw the cat alive and the you that saw it dead actually inhabit separate worlds. By that I mean, they exist in their own complete realities, and those realities will never interact. But where did these separate worlds come from? Well, something I haven't mentioned yet are all the particles of the environment, the air molecules, photons, everything that we are not keeping track of. If a quantum object in a superposition gets entangled with the environment, it is said to undergo environmental decoherence. This branches the wave function of the universe, essentially splitting the universe into two slightly different copies. So, a more realistic account of Schrödinger's cat goes like this. The radioactive atom evolves from 100% not decayed into a quantum superposition of decayed and not decayed. The detector becomes entangled with this superposition state of the atom. But the detector is being bombarded by all these air molecules and photons in the box, which would bounce off differently if it is detected radiation than if it hasn't. So almost immediately, the detector becomes entangled with the state of the environment. It decoheres, branching the wave function in two. At that moment, you are split into two identical copies, one entangled with each outcome of the experiment. You continue to be identical until you open the box, but in this case, the cat actually is alive or dead. You were just finding out by opening the box. What we are unaware of is that the other outcome also happened, just to someone who is not you anymore. I mean, both observers came from you, but they are no longer you, and they're no longer identical to each other. This interpretation of quantum mechanics is called many worlds, and it was formulated by Hugh Everett. And if it's true, the branching of the wave function is happening all the time, so frequently, in fact, that the rate may well be infinite. Creating infinite, subtly different worlds all the time may sound implausible, to put it mildly, but consider that all those worlds are naturally part of the mathematics of quantum mechanics. Many worlds just takes them seriously. To get rid of them requires something like the collapse of the wave function. And the point is, our experience of reality would be the same in the many worlds picture as it is if the wave function collapses. But the formalism is so much cleaner and more elegant. All we have are wave functions that evolve under the Schrödinger equation. The implication is that the founders of quantum theory may have got it exactly backwards. The wave function is the complete picture of reality, and our measurement is just a tiny fraction of it, the part we become entangled with when we interact with a quantum object in a superposition. The universe also goes back to being deterministic. Every outcome happens 100% of the time. It only doesn't look that way to us because we only experience our tiny sliver of the multiverse. Now, I imagine that a lot of you have questions and possibly objections to this, so I went to the expert.
Hey.
Hello. How are you?
Come on in.
Okay, so I wanted to make this video about many worlds, but I was concerned I was going to screw it up. So I've come here to meet Caltech professor Sean Carroll, who has literally written the book on many worlds.
Here's the book, Something Deeply Hidden, available wherever books are available.
Let's ask probably the common sort of YouTube questions,
Yeah.
the
Good.
arguments against this.
Yes. You know what the first
Maybe
one is?
how many worlds are there?
No, the first one is energy
The energy.
conservation. How is energy conserved is completely clear in the math. The energy of the whole wave function is 100% super duper conserved. But there's a difference between the energy of the whole wave function and the energy that people in each branch perceive. So what you should think of is not duplicating the whole universe, but taking a certain amount of universe and sort of subdividing it, slicing it into two pieces. Pieces look identical from the inside, except that one has spin up and one has spin down or something like that, but they're really contributing less than the original to the total energy of everything.
Let's ask the question about how many worlds there are, or how frequently are they branching?
Right, we have no idea is the short answer to this. And I think it's embarrassing that we don't have any idea. It's certainly often, it's certainly a lot, right? The universe branches whenever a quantum system in superposition becomes entangled with its environment. So you have atomic nuclei in your body that are radioactive. They decay 5,000 times a second. There's a radioactive decay in your body. Every one of those either decays or doesn't. You can think of it as a superposition. And once it decays, it sort of interacts with what's around it, becomes entangled, and the universe branches its wave function, right? So branching is happening many, many times a second just because of radioactive decays in your body. Now, is it happening infinitely often? We don't know, because we don't know whether the total number of possible branches is infinitely big or finite. It's humongous by any stretch. There's plenty of room for all these branches to exist, and it might very well be finite, but that the details hinge on things we don't understand about quantum gravity and cosmology and the theory of everything and all that stuff. So it's a big number, but we don't know how big.
Let's deal with the misconception that many worlds means everything that could possibly happen happens.
Yeah, that's not true. Many worlds means the wave function obeys the Schrödinger equation. That's what it means. And the Schrödinger equation predicts many things could potentially happen, but not everything. So for example, an electron will never convert into a proton. It would violate conservation of mass, conservation of charge, all of these things that the Schrödinger equation gives zero probability to ever happening.
What about you becoming president?
Yes. That could happen.
There is a world in which you're president?
There is a world, well, to be super duper clear, it would not be me who is president, it would be a version of me. Right?
But once
the branching happens, those are two separate people now.
But there is a version of you who is currently president.
Yes, that's right.
And who is tweeting.
It's a very low amplitude world. It's a very small probability, but it's there, yes.
I mean, I think this is the way in which it feels more complicated or it feels more ridiculous than Copenhagen, because Copenhagen's like, there's just one world, this is it.
That's right.
And it's what you experience.
But look, the universe, the good old universe, forget about quantum mechanics, okay? Just like the cosmological universe where we see all the galaxies and everything. We don't see the whole universe. We see a finite amount of it because light moves at the speed of light, so there's a place beyond which we can't see. The universe could be infinitely big. We don't know. It's certainly very plausible the universe is infinitely big. It's plausible that everywhere in the universe looks more or less like what we see, with galaxies and stars and the whole bit. If that's true, there's an infinite number of copies of people exactly like you. Some of them are presidents, some of them are winning NBA championships, some of them are supermodels, whatever. It's just because there's a lot of different shuffling around of the atoms, okay? It has nothing to do with quantum mechanics or weirdness. Does that bother you? Does that, rub you the wrong way?
Kind of.
I think, well, maybe it should.
but I agree it's less weird than the quantum idea.
And I think in both cases, it's because, human beings, there's some cognitive bias. I don't know what it's called, but there's a cognitive bias that says the only probabilities for anything are 0%, 50%, or 100%. And when I tell you something can happen, but the probability is really, 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 really low, people are like, but it can happen, right? Like, let me focus on that possibility that it happens. I'm like, no, don't do that. It's just not sufficiently probable that it's worth worrying about in any way. When the world branches here, does it branch instantly far away? The answer is, it's up to you. This is the annoying part of the answer. I can write down a description in which the branching happens instantly throughout all of space. I use that description to make predictions about what people will see. All those predictions come out 100% completely true. I can write an alternative description in which the branching sort of spreads out at the speed of light. And I make a different set of predictions, but guess what? They're exactly the same predictions. There's no difference between what those two pictures actually predict. And what this is reflecting is God doesn't know about branches. There's the wave function of the universe. That's all that really exists, okay? Breaking the wave function of the universe into different pieces that you and I call branches or worlds is very convenient for us human beings. But that's all it is. It's not built into the fabric of reality itself. It's just like, it's exactly like the air in this room. Rather than listing the position and velocity of every single air molecule, I just tell you the temperature and the pressure and things like that, right? It's a convenient description for us human beings. It's not the full description of the reality. And branches are exactly the same way. So if you get annoyed that there's two different ways of describing the branching, you have to remember that the whole idea of branching is just a human convenience.
Hey, this portion of the video is sponsored by Norton 360, a global leader in cyber safety. Norton 360 comes with multiple layers of protection for your devices, not just antivirus and anti-spyware, but also things like dark web monitoring powered by LifeLock. This software monitors the dark web for uses of your personal information. Now, of course, no one can prevent all cybercrime, but it's important to take a multi-layered approach to protection because cyber threats are constantly evolving. That's why Norton 360 also comes with a virtual private network, or VPN. A VPN creates a private encrypted data tunnel that helps prevent cyber criminals from hacking into your Wi-Fi and intercepting the data you are sending and receiving. This is particularly useful when you're using public Wi-Fi. I like to use it when I'm traveling. So when I'm connecting to Wi-Fis in hotels or airports or coffee shops, it just gives me that extra peace of mind. Right now, you can get up to 60% off by using promo code Veritasium or by clicking the link in the description. Now, Norton 360 has graciously given me Norton 360 Deluxe to try out for myself, and I'm really enjoying it. So I want to thank Norton 360 for sponsoring this portion of the video, and I want to thank you for watching.